Our planet is usually a ruthless accountant. Most phenomena can be traced, measured, modeled, yet scattered across Earth are places and events where the numbers don't quite add up, where the equations feel incomplete. These are not magic tricks or internet hoaxes, but genuine scientific puzzles, glitches in Earth's apparent matrix that resist easy explanation and quietly remind us how provisional our understanding still is. Let's start in a forest where rocks seem to move themselves. Across the world, from California's racetrack playa to remote Canadian lakes, people have found walking rocks and logging stones, heavy boulders that leave long, sinuous trails in mud or on dry lake beds, as if they had slowly slid across the ground. For decades, no one had ever seen them move. Only the tracks remained. The leading explanation at Racetrack Playa is elegant. In winter, a thin sheet of ice forms under and around the rocks. When sunlight weakens the ice and a light wind blows, the ice rafts drift, gently pushing the stones and carving tracks in the soft sediment beneath. GPS tags and time-lapse cameras finally caught this in 2013. But here's the glitch. That mechanism doesn't neatly explain every case. Some trails curve sharply, cross each other, or climb slight slopes where wind-driven ice should struggle. In other locations, like forested lakes with no broad ice sheets, stones still seem to migrate over years. Alternative ideas involve freeze-thaw cycles, subtle soil creep on very low-angle slopes, or even micro-earthquakes that repeatedly jiggle the ground. Each can work in specific conditions, but none universally fits all observed tracks. So we're left with a phenomenon that is mostly explained in one famous desert, yet only partly mapped elsewhere. A reminder that even something as simple as a rock on mud can hide a surprisingly stubborn mystery. Now, from wandering stones to a sound that should not exist. In 1997, the US National Oceanic and Atmospheric Administration recorded a bizarre noise in the Pacific Ocean. It was a low, rising bloop that lasted about a minute, detected by hydrophones thousands of kilometers apart. To be audible over that distance, the source had to be enormous. At first, its frequency pattern looked eerily biological, like the call of a living creature, just scaled up far beyond any known whale. The internet did the rest, spawning legends of colossal sea monsters. Later analyses suggested a more mundane culprit: icequakes. When massive Antarctic ice shelves crack or collapse, they release acoustic energy that can propagate through the ocean as low-frequency sound. Several recorded ice events produced signatures similar to the bloop. Yet the bloop still sits in a gray zone. The location triangulated to a remote point in the South Pacific, far from major ice fronts. The signal was unusually loud, and its frequency sweep didn't perfectly match known icequakes. Crucially, the ocean is undersampled. Our hydrophone network is sparse, and most of the deep sea is acoustically unmonitored. That means we have a tiny library of known natural sounds and a vast space of unknowns. The consensus today leans toward an ice-related origin, but with low confidence. The bloop is probably not a leviathan, but it is a data point from a soundscape we barely understand, a reminder that the deep ocean is still, in many ways, acoustically alien territory. Some glitches feel almost like optical illusions written into the landscape. All over the world, so-called gravity hills or magnetic hills appear to make cars roll uphill and water flow the wrong way. Park your vehicle in neutral, release the brake, and it seems to defy gravity, slowly climbing what your eyes insist is an incline. The standard explanation is psychological, a forced perspective trick. Without a reliable horizon, our brains misjudge slopes. Trees leaning slightly, curved roads and surrounding terrain can make a downhill grade look uphill. When surveyors measure these sites with precise instruments, they almost always find that the uphill direction is actually a gentle descent. Yet there are a few locations where the story is not perfectly closed. Some measurements show gradients so close to flat that the expected rolling speed from gravity alone is tiny, yet objects accelerate more than predicted. In rare cases, compasses behave oddly, hinting at local magnetic anomalies from iron-rich rocks or buried ore bodies. Could subtle variations in Earth's gravitational field caused by dense rock bodies underground, be detectable at human scale? In principle, yes. Gravimeters can measure such differences, but they're far too small to make a car roll uphill. So while most gravity hills are well understood illusions, a small subset still invite more careful geophysical surveys. They're not portals or broken physics, but they are places where our sensory system, local geology, and measurement precision collide in ways that keep scientists from closing the file completely. Some glitches are not about motion or perception, but about life itself appearing in the wrong place. In the Venezuelan highlands, flat-topped mountains called tepuis rise like islands in the sky. On one of them, scientists discovered a tiny black frog about the size of a fingernail that seems to break several rules at once. It's called Oreophrynella nigra, and its closest relatives live far away, separated by deep valleys and millions of years of erosion. Genetic studies suggest these frogs diverged long ago, yet their current distribution doesn't neatly match models of how the tepuis eroded and isolated. It's as if evolution's branching tree has a few branches that don't line up with the geological timeline. This is not a single odd frog problem. Biogeography, the study of how species are distributed, is full of such glitches. Plants in South America that are strangely close relatives of African species, cave organisms that appear in isolated systems with no obvious migration route, microbes in deep rocks that share genes with surface species they should never have met. We have tools, plate tectonics, ancient climate reconstructions, DNA clocks that estimate when species split, but these tools have error bars. Mutation rates vary. Fossil records are incomplete. Erosion can erase entire landscapes that once connected habitats. So when a species shows up in a place evolution didn't seem to plan for, it's not that Darwin was wrong. It's that our reconstruction of the past, the exact routes, timings, and barriers, is still pixelated. Each impossible distribution is a glitch that forces us to sharpen that picture. Other glitches are written in the sky. On June 30th, 1908, something exploded over the Tunguska region of Siberia with the energy of 5 to 15 megatons of TNT, hundreds of times the Hiroshima bomb. It flattened about 2,000 square kilometers of forest, yet no impact crater has ever been found. The leading explanation is an airburst. A stony asteroid, maybe 50 to 60 meters across, entered the atmosphere at tens of kilometers per second, experienced intense aerodynamic pressure, and disintegrated at an altitude of around 5 to 10 kilometers. The resulting fireball and shockwave did the damage without leaving a classic crater. Computer simulations support this. We've seen smaller airbursts like the Chelyabinsk event in 2013, where a 20-meter object exploded in the atmosphere and shattered windows across a city. But Tunguska still has loose ends. No definitive fragments had been recovered. Tree fall patterns are complex. Some eyewitness accounts mention strange lights and multiple booms that don't perfectly match simple models. Alternative ideas, a comet made mostly of ice, or even an unusual atmospheric plasma event, have been proposed, but each struggles with the energy budget and the observed devastation. Tunguska sits in a category of probably solved, but not fully nailed down. It's almost certainly a cosmic impactor, yet the exact composition, trajectory, and breakup physics remain fuzzy. In planetary defense terms, that fuzziness matters, because understanding Tunguska-scale events is key to predicting what future airbursts might do. Let's end with a glitch that happens all the time, right above our heads, and still defies complete explanation: lightning. We know the basics. Thunderclouds act as giant charge separation machines. Colliding ice particles and supercooled water droplets transfer electrons, building up regions of positive and negative charge. When the electric field becomes strong enough, on the order of millions of volts per meter, it overcomes the insulating properties of air, and a lightning discharge occurs. But zoom in and the picture gets weird. Lightning doesn't travel as a single clean bolt. It advances in jagged steps, called step leaders, that propagate in bursts of tens of meters at a time, pausing between jumps. The exact microphysics of how these leaders form, branch, and choose a path through a chaotic electric field is still an active research area. Then there are the real glitches, phenomena like sprites, blue jets, and terrestrial gamma-ray flashes. Sprites are enormous, ghostly red discharges that bloom above thunderstorms, reaching up toward the ionosphere. Terrestrial gamma-ray flashes are bursts of high-energy photons, gamma rays, produced in the atmosphere during storms, detected by satellites usually built to watch cosmic explosions. How does a thundercloud, only a few kilometers tall, accelerate electrons to relativistic speeds, close to the speed of light, strong enough to emit gamma rays? Several models invoke runaway electron avalanches, where a few high-energy electrons, accelerated by strong electric fields, knock others free in a chain reaction. But the exact conditions that trigger these avalanches and how they couple to ordinary lightning are not fully pinned down. Lightning is a daily, global event, yet its most extreme behaviors remain partly unexplained. And that may be the most important glitch of all, the reminder that even in the familiar flicker of a storm, Earth is still running code we haven't fully debugged, and that the next layer of understanding is always waiting, just beyond the edge of what we think we already know.